So, our next speaker is Professor Yi Cui at Stanford University. He's in the Department of Material Science and Engineering, and he received a bachelor's degree in chemistry in 1998 at the University of Science and Technology of China, and PhD in 2002 at Harvard University. After that, he went on to work as a Miller postdoctoral fellow at UC Berkeley, and in 2005, he became an assistant professor in the Department of Material Science and Engineering at Stanford, and he was promoted with tenure in 2010. His selected awards include MRS Medal, Dan Maiden Prize in Nanoscience, Nano Today Award, and a numerous list of prestigious awards. So without a further ado, it's my great pleasure and honor to welcome Professor Yi Cui to the stage, Zoom stage we prepared. Professor Cui.
Can you see my slide?
Yes, perfect. So please.
Okay. Well, let me thank Edu Kim for the invitation. This is very nice conference. I listened to this conference yesterday. John's talk, Zhennan's talk, and Yonan's talk. So Bing's talk continued this excellent trend. Let me now switch the topic a little bit. Bing already touched upon some of the battery work. I'm going to tell you about the research in my lab. We try to reinvent the batteries through materials design and the new tools. Batteries are so important, so no need to reconvince you for portable energy storage as well as stationary. And from yesterday's talk, from John's talk and also Zhennan's talk, you also see in the wearable electronics require wearable batteries as well. The importance of batteries, I would say the past 40 years of development, this is a very well-deserved Nobel Prize in Chemistry to John Goodenough, Stan Whittingham, and Yoshino. They are the pioneer to develop the lithium-ion batteries, enable portable electronics as well as the electrical cars coming. Now the question is, after this, what's next? What are the grand challenges remaining for the batteries to solve? Well, I will call this as a battery 2.0. A question worthwhile for the whole research field to think about. So one question we ask is how high of the energy density the batteries can go per unit weight or per unit volume? Can we double or triple of the energy density? And can we extend the battery life a lot longer, both cycling life as well as the calendar life? How fast the batteries can be charged? Can we do less than 10 minutes or even 5 minutes? This has huge meaning to the whole application field. This will speed up the the green revolution if the car can be charged within 5 minutes, and this has huge impact to the deployment of the electrical cars. Can we make the batteries safe completely and without catching fires? And can we reduce the cost down by 3 times? This will help for implementation of the electrical cars as well as grid-scale energy storage. How do we sense the battery health condition and know what's going on inside? So far, battery sounds like a black box right there. And what are the strategies for battery reuse and recycling? How do we do grid-scale and seasonal storage? And how do we make batteries valuable, flexible, and stretchable? So many of this really, I think all these questions, anyone you could solve and will mark as a big breakthrough for the field. So over the past 15 years at Stanford, my group has tried to work on many of these challenges. I just want to share with you, some of them, how we reinvent the batteries to, enable the future potential, particularly on the high energy density batteries. What I list right here, if you look at the vertical axis, is the relative volume change. Horizontal axis is the amount of lithium you store versus the host atomic number. And the past 40 years, we have been playing with lithium iron phosphate, lithium cobalt oxide, right, graphite, And the lithium to the host atom is roughly 1 to 6 to the left of this plot. And with more and more energy putting in, you need to put more and more lithium ions going in. And so the amount of volume change will go up tremendously. And these create huge problems for us to handle. How do we solve this problem? But if we could do that, from the past, it's a stable host with the new materials, new hosts coming in. And there's a significant bond breaking, and host atoms move to long distance, complete structure change on the right, and large volume expansion, 10 times or more. And how do we solve this problem? This really requires us to have a paradigm shift of material design, considering the challenging in the atomic scale to nanometer scale to the whole electrode scale and then to the whole cell. This has been a big challenging for the many years. People work on batteries. So if we could do that, the high energy density becomes possible using graphite with MMC nowadays in the bottom of this graph, 250 watt per kilogram also, to silicon with MMC, to lithium metal with MMC, and lithium metal with sulfur. You could potentially enable the energy density doubling or more if we know how to make these new chemistries to work. They have a very large volume change, a very big structure transformation. So a well-known example is silicon. Silicon stores 10 times more lithium than the graphite carbon, but silicon also expands 4 times. This creates huge stress. It can, from taking a particle, volume expand, the stress is too big and it causes materials breaking. Once the materials are broken, and you lose electrical contact, and you cannot keep shipping electrons in, take electrons out anymore, and you create more surface area, react with organic electrolyte, and having more and more of the solid electrolyte interface, so-called SEI. So this has been a big challenges to the whole field. And about 13 years ago, when I started to work on silicon, and we published this first paper and using silicon nanowires, and they are growing off the metallic current collector, and you can ship the electrons in and take the electrons out directly. This maintains direct electron contact, and the diameter of the nanowires are small enough, and our hypothesis is it could relax the strain fast, will not break. And also there's space between each of these wires to have the volume expansion without breaking. So this concept really kicked off the whole research field of using nanotechnology, nanoscience design to impact the batteries field. So I want to share with you is during this process of material design, we need new tools to look at how the batteries work. We were one of the earliest group to adopt in situ TEM of electrochemical cell, and to build single nanostructural battery inside the TEM. So in this TEM holder, we can mount a silicon nanowire, can plug into the ionic liquid, and lithium cobalt oxide is the cathode. Now you can cycle this battery by applying electrical current. Electrons comes in, lithium diffuse into the nanowire, charge neutralized with the electrons, and start to react with silicon. You can watch this process under TEM to really learn a lot about the size effect of this nanostructure, how these materials are broken. This is in collaboration with my colleague Bill Nix. Matt was my one of my graduate students, now a faculty member in Georgia Tech. We can also put particles onto these wires. You can lithiate, react with the particles as well to watch this whole process happening. So here I want to show you an in situ video of silicon nanowire with lithium coming in. The volume expansion is taking place, and the surface coating look like black color, and the copper coating is broken, but the nanowire does not break. So this scale bar right here you are seeing is 200 nanometers. So these wires has a diameter about 200 nanometers to start with. The volume expansion is taking like crazy. Right? This is a speed up by multiple times for you to see. And using this technique, we can also look at different size, different morphology. For example, silicon nanoparticle in the middle you are seeing is 800 nanometer in diameters. Lithium comes in, the volume of this particle is expanding. After a while, this particle accumulates so big of stress and it's going to be broken. You can see the core of crystalline core, it is amorphous shell right there, lithium coming in, really break the silicon and silicon bonding and made the amorphous lithium silicon bonding. So this change is very, very dramatic. Using the tool like this, we are able to identify what's the critical breaking size for the silicon, and the diameter smaller than about 150 nanometers. These particles do not break as that easily. Above that, they break more. So it is a detailed stress analysis in this publication in Advanced Materials, and this really provides a guideline for the whole industry to design what's the size of the materials we need to avoid the breaking. So over the years, we have been through the design of nanowires and core shell structure and hollow, double wall hollow, and yolk shell, and silicon hydrogel, and self-healing thinking, pomegranate type of structure, try to reduce the surface area of silicon nanoparticle forming these secondary particles. And this has been 12 generations by now. This is really guided by the problem as well as the tools we use to understand the problem happen in silicon anode. Let me share with you, this Yolk-Shell design of this nanoparticle as the yolk. The shell is carbon. We designed this empty space inside this hollow carbon just right, and we can. Let me turn on the video. So maybe it's harder to play this video. Let me just play the also the generation 12 of design. Put this nanoparticle together. If you go through the battery manufacturing process, it requires high pressure calendaring process. The secondary particle can be broken easily. So we designed a shell protected secondary particle, coating the secondary particle outside shell with a layer of a crust that's mechanically strong, can take on this mechanical pressure. Let me show you this the video of the silicon cluster press under the mechanical indentation. The left-hand side is there's no this crust you can see, and this nano indenter inside SCM will break this particle. But the right-hand side with silicon CVD or shell right there will keep the whole structure together to have only elastic deformation. So using this design, we can take on the pressure as high as 100 megapar, and that really allow us to stabilize this particle for calendaring to make the real electron improve the battery performance. So silicon, as we are speaking, is really starting to go into the commercial world. About a decade ago, 12 years ago, I founded Amprius to commercialize our silicon nanowire technology along with other silicon technology. Amprius is making very high energy density of battery now using the commercial drone and Airbus, and also many of other actually customers started to use Amprius high energy density batteries. This continue to be exciting. Amprius will need to do a good job. Next is to enable the low-cost manufacturing to reduce the cost further. Then that will be able to go into the electrical car application. So with this silicon design, the holy grail of the battery is really the metallic lithium anode. Metallic lithium anode has no host. It's just lithium metal by itself. So during the charging, it will go through this electrodeposition process. During this charge will be electrochemical stripping. So during this process, the thickness change of the electrode is very dramatic. In this perspective article we published in Nature Nanotech, we point out to the community saying this volume change is too dramatic. There's no holes. The relative volume change is infinite. And then the interface, because the solid electrolyte interface right there, this plating cannot be guaranteed as a flat plating layer by layer. You're going to cause the surface morphology change that will break the SEI. Once the SEI is broken, you will create a hotspot that will grow out this metallic lithium dendrite, cause the battery shorting. And so this is really, really challenging a problem. Remember, every time if you need 3 milliamp hour per centimeter square capacity, that's common in the battery cell. It's a 15 micron of lithium plating. And then when you do stripping during discharge, 15 micron is gone. So for each layer of electrode, this 15 microns up and down is too much. So indeed, we share with the whole community in saying the root causes of the problem in the center. One is infinite volume change in the relative sense. And the second is really high chemical reactivity of lithium with the electrolyte, cause all the surrounding problem we observe when we made the batteries and do the measurements. So in order to solve this root causes problem, and we come up with a strategy working in collaboration with Steve Chu and Zhenan Bao at Stanford right here. To the left, we propose for the first time of stable host for also lithium metal. In the past, lithium metal people use is just a foil. We learned from the graphite how graphite will work. Graphite is the host for lithium ion. We could construct hosts, but the host will be very different from metallic lithium. In 2016, we published several papers to really propose and demonstrate for the first time of metallic lithium host. Now, many research groups around the world is using the host concept for metallic lithium and also metallic sodium, other metallic anode. And then the interface is also very important. What's the nature interface we want? We want it to be mechanically strong, mechanically resilient, as well as chemically stable. Remember, lithium metal is so reactive. Without mechanical and chemical stability right there, you will not be able to have a stable interface. So let me share with you some of the examples of design. First of all, how does the lithium plating happen? We use all type of substrate, right, for lithium plating, and when we build the batteries, for example, copper is commonly used. We find out on copper surface, lithium plating has overpotential. You see this voltage dip and lithium nucleation and then plating happening. And then on some other substrate, on gold, for example, the first plateau at 200 milliwatt is the lithium gold alloying, and then the second plateau and then the lithium plating happen close to the zero potential. In this case, you don't see the voltage dip anymore. So you really don't have the lithium nucleation barrier right there. So this is very different. Copper and gold, the differences are just gigantic. It's due to the phase diagram. If you look at the top, it's between copper and lithium. Bottom is gold and lithium. Look at the most right-hand side of the phase diagram. Copper has no solubility in lithium, but gold has solubility, the tiny zone to the right. And this is really telling us once lithium coming in, deposit onto gold, alloy with gold, first alloy phase, second alloy phase, and then lithium coming in, continues coming in, it will have the ability to dissolve gold away. However, lithium cannot dissolve copper away. And once lithium dissolves gold away, lithium make gold and more look like lithium before lithium deposition happening. There's no overpotential for the case of gold. So using this idea, we are building a host for the first time. It is hollow carbon. We actually screen all type of hosts. We find out lithium has nucleation barrier on carbon, and lithium would not like to nucleate directly onto carbon. if we build a hollow carbon host and put gold nanoparticle in the middle, and once we deposit lithium, lithium will like to diffuse through, lithium ion diffuse through this carbon shell and deposit inside of this hollow carbon. Now we can control spatially lithium will go, and this carbon shell will function as a solid electrolyte interface to isolate lithium from the organic electrolyte. And we made this structure using TEM to confirm that. And this in situ electrochemical cell cycling, we want to show you this gold nanoparticle now inside this hollow carbon sphere. We put lithium in, you can see lithium dissolve, gold away. It has the ability, confirm our hypothesis based on the phase diagram. And then once you strip lithium away, and the gold nanoparticle comes back, but at different location though, it also breaks into some tiny particles instead of initial one as a single particle. This is confirmed. You strip lithium away, this gold kind of supersaturated and precipitate out. They can have multiple nuclei right there. So using the seeded hollow carbon at the bottom, after depositing some capacity, you don't see filamental lithium growing out of this hollow carbon. However, for the hollow carbon alone on the top, without the seed right there, you see this filamental lithium structure, the deposition going out. This will get in touch with electrolyte. They're going to react with electrolyte. So the top case will be less stable. The bottom one present a lot more stability. So with this initial demonstration, what we really want to have to already using chemical synthesis to embed metallic lithium into the host. We developed a molten lithium infused process for the first time in 2016 by these two graduate students, now postdoc in the East Coast. So we melt the lithium, try to use all type of carbon host, carbon nanotubes host, lithium metal after melting. It does not like to wet. All type of carbon, they don't want to wet until we try graphene oxide. Graphene oxide wets lithium very nicely. Apparently, there is a wetting phenomenon right here, so similar to water's wetting, hydrophobic and hydrophilic. For the lithium case, we call the new term lithophilic and lithophobic. Lithophilic describes a wetting phenomenon of molten lithium. And the reason graphene oxide allows lithium metal to wet is because it has all this polar functional group. And lithium reacts with the OH and functional group, for example, and the delta G of the reaction is negative. So it's actually a wetting surface. And the gap between the graphene oxide is a capillary, there's a capillary force interaction right there, pulling molten lithium going to the graphene oxide. And indeed, we don't have to use a heavy weight of graphene oxide. It's only 8% by weight. So you don't reduce the lithium metal, a high capacity that much. It's still very, very high. So this graphene oxide made by filtration, put into molten lithium, you will see a spark reaction happening, opening up the gap to tens of nanometers to hundreds of nanometers. Lithium metal embedded into the graphene oxide through the capillary force. If you look at the cross section, before the spark reaction on the top, and then after spark reaction, the gap opening in the middle, after lithium infusion, it looks very nicely embedded, hosting between the graphene oxide. So using this idea, if you imagine you do stripping, you take lithium out, as long as you have a little bit of lithium, you are going to hold the space between graphene oxide, holding the volume. So the whole volume of the graphene oxide with lithium metal composite will not change that much. If you stabilize its dimension, now you have the opportunity to build stable HCI. So we demonstrate that there's no dendrite growth in this case. Then we further ask the question, you can have horizontal graphene oxide. What about we can align the graphene oxide vertically? What will be the difference? Because lithium needs to transport through this graphene oxide, going to deposit inside. If you have vertically aligned your tortuosity will be 1. If you have horizontally aligned, your tortuosity will be high. So vertical tortuosity will reduce the ionic resistance, the bottom row right there. And the plating of lithium metal onto this graphene oxide back and forth will be more uniform. We think the bottom will be better. So my postdoc Hao Chen recently demonstrated we use this method of graphene oxide aqueous solution and then freeze it. And once you freeze that, you can align this ice crystal and graphene oxide will be aligned. So we can align it vertically, that's on the top row. Middle is horizontally. We can also have a kind of beaker to freeze from the side. Then you align this radially, you have this random orientation. So this SEM image is really showing you the vertically aligned, horizontally aligned, and randomly arranged graphene oxide. Use that to do lithium plating and stripping. If you look at the red color plot, that's vertically aligned Coulombic efficiency, stability. The vertically aligned is better than the random aligned. Random is better than the horizontally aligned. It's actually very, very strong correlation right there. And from the morphology, if you look at the top row of SEM, from the horizontal align, random align to the right-hand side vertically VGA. VGA has this dense lithium plating going to the graphene oxide, reduce the surface area of lithium metal, reduce so-called mossy lithium, and the stability of the vertical align is better. If you look at tortuosity, we measure it. Horizontal align having high tortuosity, about 4.5. Randomly aligned is about 1.8, but vertically aligned is about 1.2, 1.3. So this very strong correlation of tortuosity affecting the plating stability. So with these, the host material design, of course, interface is very important. Over the years, we developed a number of interfacial materials, try to stabilize metallic lithium anode. And one idea, of course, to generate very stable interface would be through, electrolyte, picking the right electrolyte, reacting with this lithium metal, and that decomposition compound can stabilize this SEI. So working together with Zhenan Bao as chemical engineering at Stanford, and our joint student Hansen Wang and Zhao Yu, and we look into this new solvent, very exciting. That's in the highlight as FDMB to the right. DME is an ether solvent used in the existing electrolyte for lithium metal. It has a reasonable stability versus lithium, but it gets oxidized by the cathode, not stable. It's very challenging to be used for the real lithium metal batteries. Then you can increase this middle hydrocarbon chain from 2 to 4. It's become DMB, that's in the middle. Stability becomes better, but still not stable enough. Adding fluorine to the central 2 FDMB, and it's become FDMB. And it turned out to be this is a new molecule. It doesn't exist before. And Zhao did the synthesis of this molecule. We use that for the solvent. If you look at figure D right here, using a FDMB as the solvent with LiFSI salt, you scan to the high voltage to the cathode side. It's strongly against oxidation, become a lot more stable. Now use as an anode, that's a figure E. The Coulombic efficiency, you deposit capacity and then you strip it away, and it becomes much higher. It becomes one of the record type of performance of electrolyte. Using a method, so-called Arbor method, to cycle this, we discover 99.5% Coulombic efficiency. It's a record high Coulombic efficiency. So we look into this further, and it built a very different morphology of lithium metal. If you look at C and D on the top, the SEM, the top view, it grows this lithium metal grain much bigger. If you use other electrolytes, this lithium dendrite, filamental lithium reacting with electrolyte a lot. So the FDMB one is much better. And using the Cryo-EM, we can stabilize the SEI solid electric interface, we also find that it's more uniform. There's also other reason why this new electrolyte is so good. And through the simulation, we find out this electrolyte in collaboration with Chen Chen in chemical engineering right here at Stanford and with his postdoc. And this oxygen and fluorine and this FDNB molecule can coordinate with lithium. If you look at figure A right here, that color, brown color electrolyte is FDNB one. Usually lithium electrolyte shouldn't have color, but because of this rim patterning of coordination, and it generates very different effect. And we also find out this coordination actually have the anion, a lot of anion coordination in the solvation shell as well. So once it decomposes to build the SEI, and it has anion-rich SEI, that's more stable for the lithium metal deposition. So more to come and explaining why this electrolyte is good. We will have another new publication hopefully coming out soon to explain this in detail. Through all this research, it becomes very clear to really understand the battery material and the interface, we need a new tool. Because the battery materials, most of them are not stable. The solid electrolyte interface is so important, they are not stable. For example, if you look at this lithium dendrite, just zoom in, just hold on, look at right there, you can see you destroy this metallic lithium. There's no way you can obtain atomic scale resolution imaging using this room temperature SEM, TEM. And we really like to solve this problem. 3 years ago, my group published the first paper, really learning from the biological field. In 2017, the Nobel Prize in Chemistry was given to a Cryo-EM study, to Cryo-EM microscopy, to study the biological molecule, solving the protein structures and so on. There's several key things right there. Is freezing the sample, freezing protocol, maintain the sample in the intrinsic state. And then the imaging condition with the using direct electron detector, using low dose to do the imaging. And collecting this protein molecule, thousands of those images with the imaging processing technique to solve the protein protein structure with now high spatial resolution, less than 2 angstroms, spatial resolution. Very impressive. So we are the first group adopted this technique, starting to work on it in 2016. And published the first paper in 2017 on the battery field. My 2 graduate students, Yanbing and Yu Zhang, take on this challenge. Yu Zhang just joining UCLA faculty after graduation from my lab. And they developed this, the cryo transfer technique, freezing, we deposit the lithium dendrite onto the TEM grid, and then plunge free into liquid nitrogen, and freeze that very fast. And developing a cryo transfer without exposing to the air. That's very important. Make sure you don't expose to the air. Transfer into the TEM. And this TEM holder is cryo holder. We have liquid nitrogen through this cold finger. Maintain the sample close to liquid nitrogen temperature. So using the cryo-EM technique to the lab, you see we are monitoring the dose rate. For the first time, we were able to resolve stable lithium metal dendrite. Do the dose testing, it can last for multiple minutes. We obtained the atomic scale resolution of metallic lithium for the first time, and identified the lithium dendrite growth orientation, crystallography orientation. We see 3 different orientation right there. Identify why it like to grow along certain orientation, because this interfacial energy with the electrolyte, with the SEI, like to have 110 to be the stable, sideward interface. So it favors certain growth direction. Most important thing is we could now have a tool to stably look at solid electrolyte interface. In the past, there are 2 proposed model for so-called SEI. One is called mosaic model at the lab. It's this patch of different components on the anode. This is the composition compound of the electrolyte. The right-hand side is the layer model. It's inorganic layer close to the anode, and then more the organic layer on the top. So there's two proposed model. If you look back, there's a few decades of a debate about what kind of model, what kind of structure SEI would have. We were able to resolve this kind of debate, a few decades of debate. We found out using EC and DEC electrolyte. You can see the left-hand side, the metallic lithium on the top, and then this white color line indicate the interface line between SEI and then lithium metal. The structure looks like is this inorganic nanoparticle embedded into amorphous matrix. Presumably, that's more of the organics right there. So this is more like a mosaic model, but we like to use a term called matrix model to describe this. This is using ethylene carbonate, diethyl carbonate electrolyte, but as soon as you add in fluorinated carbonate as an additive, this is commonly used in the batteries, and the whole SEI structure change become the multi-layer model, lithium metal in the bottom, and then having a amorphous layer. And then on the top, you see this beautiful lattice fringe. That's the inorganic lithium oxide cover on the top. So it suggests it's a multi-layer model. So both Dolong Alba proposed multi-layer model and Palais proposed the mosaic model. They're both right. We have slight modification. The multi-layer model right here is is inorganic on the top instead of in the bottom. So it's inverse a multi-layer model. So this is first time we could clarify the SEI structure. So the Cryo-EM will serve as very important tool in the past 3 years. Through my group demonstration, we have seen many time is the first time we observe something that's new, explain the mystery and the batteries as well as a metal organic framework, perovskite solar cell. I believe the Cryo-EM will be a very powerful tool for people to use to really discover the exciting problem in their field, including, for example, catalysis. Recently in ACS Nano, we wrote this perspective article thanks to Paul Weiss. This paper came out recently. We spent quite a bit of time to share with the whole community what Cryo-EM could do to the batteries, to the catalysts, MOF, perovskite, quantum materials, and soft materials. I encourage you to read about this perspective. We put in many ideas we think the Cryo-EM can do. Well, let me end my talk by thanking many talented graduate students and postdocs, and thank the funding support, particularly from DOE, ERE, Vehicle Technology Office, Battery 500 Consortium, and Battery Material Research Program, and also DOE BES Material Science Division to fund us, particularly on the Cryo-EM research. Thank you very much for your attention. I will be happy to take any questions you have.
Thank you, Professor Yi Cui, for your very nice talk. Indeed, we have a few questions posted in the Q&A chat box. So let me read it for you. The first one is from Dongha Kim. He said, great talk regarding to molten lithium incorporation into carbon matrix, particularly RGO. Have you considered using of holy graphene with abundant small holes for better lithium diffusion and penetration of materials?
I think that's a really great idea. We haven't done it, but I think it's a great idea. Yeah, for sure. This would help a lot to reduce the tortuosity. Somebody, I think, must have a holy graphene, right, looking in the literature. So that could be a good thing to try.
Okay, thank you. The next question is by Jechul Chue, and he said, thanks for the nice talk. A simple question on RGO molten lithium, RGO/molten lithium electrode. It seems that the high surface area of RGO may lead to consuming more electrolytes, particularly for the initial cycle. How was the charge-discharge efficiency over cycles?
So I think that's a good question. So eventually the goal will be, if we use for RGO, you still want to do a surface modification to reduce the exposed surface area to the electrolyte. That will be the way to go. And Otherwise, I think the first cycle, even you just soak in the electrolyte, it's going to react. If you have the right electrolyte component, that might also work. It form automatically a good SCI pathway that. Then down the road, your volume change will be small. If you can guarantee that, then it might also serve the strategy because you already have a lot of lithium in there. You're going to sacrifice some. That's possible. And as long as you don't have big volume change anymore, you could still stabilize that interface.
Thank you. The next question is by Taewon Kim. He said, thank you for your impressive talk. I have one question. Any 2D material with good conductivity and lithophilic, such as Maxine, can be good lithium host material? It's with ending with a question mark. Are there any other design rule for good lithium host materials?
So Maxine potentially is also a good host. And it's but precondition needs to be stable chemically. I think the design rule will be you need to have some polar functional group. So lithium metal can wrap in there. The delta G needs to be negative. The reaction between lithium metal and the functional group. Then after that, it needs to be chemically stable. If it's not stable, make sure the reaction product still maintain the adequate mechanical strength and holding the whole structure right there.
Okay, let me see. We still have, there is another question here with Baekal Che. Multi-layer can be strong as real using conditions in car or ETC? I think that's a question mark, yes.
Say the question again.
Multi-layer can be strong as a real, I'm not sure if I understand this question as well. Using condition in car or ETC. So that's in the Q&A chat box. Can I ask the Mr. Chue to specify your question? Can you specify it? While he specifies his question, I also have one quick question for you. So you showed great results and findings and your way of thinking to the innovation. Here at KAIST, we are also interested in educating our students to have entrepreneurship. And you already showed that early in 2010 or 11. So do you have any advice to professors here or students here, how we can motivate students or professors to create venture business out of the findings we discover at the lab?
Yeah. I think I'm relatively familiar with Korean. I think and KAIST, right? There's a lot of exciting research and very creative people right there. Probably KAIST, around KAIST need an ecosystem. I don't think it's lacking of idea. It's probably you require a financing mechanism, need a vibrant venture capital community right there. Then forming the startup can become possible.
Okay, thank you very much. So in the interest of time, even though we may have more and more questions, we will have to leave it here. And I'd like to thank you again for your precious time and wonderful talk. Thank you.
Yeah, thank you.